The boiler sits in the center of the mill like a heart no one dares approach too closely. Iron plates sweat under the weight of pressure building inside them, steam climbing past 100 pounds per square inch, clawing against rivets hammered into place by men who are long since dead. The furnace door glows with a dull orange pulse. Every few seconds, the fireman swings it open, shoveling another cascade of pine scrap and resinous bark into the roaring throat. Sparks scatter across the floorboards, briefly illuminating the machine's broad steel belly. The gauge needle trembles. Above the boiler, a web of pipes screams with heat. Steam surges outward to drive the mill's line shaft, a rotating spine that powers everything. The screaming circular saws, the carriage that drags whole trees through spinning steel teeth, the conveyors carrying lumber toward stacks that rise like wooden city blocks along the riverbank. 30 men are working inside the mill this morning. Sawyers lean into their stations, faces powdered with yellow dust. Log turners shout over the thunder of machinery. The carriage operator grips a lever polished smooth by years of use. But every man inside the building knows the same truth. If the boiler fails, none of them will outrun it. There is no shield, no blast wall, no reinforced housing, just riveted steel plates separating hundreds of gallons of superheated water from a crowded wooden building packed with workers. The boiler groans as the pressure climbs. A rivet head shifts slightly, barely visible. The fireman wipes sweat from his face and throws another shovel of fuel into the furnace. In the sawmill ledger, the machine is simply listed as boiler number 3. Among the men who work beside it every day, it carries a different name. They call it the Widowmaker, power that could kill its masters. The steam boiler transformed the sawmill from a seasonal enterprise into an industrial engine that never slept. Before its arrival, lumber production had moved at the pace of rivers and wind. Water wheels turned only when the current was strong. Log drives waited for spring melt. Entire towns paused when winter froze the channels that carried timber downstream. Steam ended that dependency. With a boiler roaring at the center of the mill, the machinery could run in any season, at any hour. The circular saws did not need daylight. The carriage that hauled massive logs across the cutting bed could operate through rain, snow, or darkness. Steam drove the belts, the gears, the iron shafts that transmitted power across the entire structure. Production multiplied. A single steam-powered mill could cut in one day what earlier water-driven operations struggled to produce in a week. Timber barons saw forests not as distant resources, but as fuel for expansion. Every additional pound of steam pressure meant more force driving the saws, faster cuts, and a greater mountain of lumber stacking along the riverbanks ready for rail shipment. But the same pressure that powered the mill also carried a silent threat. Inside the boiler, water was heated far beyond the point of ordinary boiling. Under confinement, it remained liquid while storing enormous energy. The moment that pressure escaped containment, the superheated water would flash instantly into steam, expanding violently, releasing force equal to an artillery blast. Engineers understood this. Even in the earliest decades of steam industry, boiler explosions were known with grim regularity. Newspapers reported mills torn apart, locomotives shattered, riverboats reduced to drifting wreckage. Entire crews vanished in bursts of steam and iron fragments. Yet the sawmills continued to install the machines in the same way. A steel boiler weighing several tons would be placed directly inside a wooden building packed with workers and machinery. It sat only yards from the saw carriage and the sorting tables where men handled freshly cut boards. Often, there was no blast wall, no brick enclosure, no reinforced barrier between the pressure vessel and the crew surrounding it. The reasons were not mysterious. Shielding a boiler required masonry, extra construction, and space. A protective structure meant thicker walls, greater cost, and a longer delay before the mill could begin producing lumber. Timber companies operating on the expanding frontier preferred speed. A mill had to rise quickly. Forests were vast but temporary resources. Once the surrounding trees were cut, the operation would move on. Investors demanded profit before the timber ran out. Under those conditions, safety improvements that slowed construction or reduced output rarely survived the accountant's ledger. So the boilers remained exposed. Firemen shoveled fuel into furnace mouths only a few steps from moving saws. Carriage operators worked within direct line of the pressure vessel's steel shell. Crews stacked lumber under rafters that vibrated with every surge of steam traveling through the pipes above their heads. The machine that powered the mill also hovered over it like a loaded cannon. Workers knew the stories. They had heard about mills where boilers launched through roofs like artillery shells, tearing through timber beams before crashing into nearby rivers. They knew about crews killed instantly when iron plates shattered into razor-edged fragments that scythed across the mill floor. Still, each morning the fires were lit. Steam pressure climbed. The saws began to turn. The line shafts whirled into motion. Logs rolled onto the carriage rails. Men leaned into their work, trusting the riveted cylinder beside them to hold together for one more shift. The paradox defined the entire industry. The boiler made the lumber empire possible, and every hour it ran, it threatened to destroy the men who depended on it. By the middle of the 19th century, timber was no longer merely a building material. It had become the structural backbone of an expanding industrial civilization. Cities were rising at a pace no generation had ever witnessed. Railroads carved corridors across continents. Mines required endless timber supports to keep tunnels from collapsing. Ships, warehouses, bridges, factories, and entire neighborhoods demanded lumber in quantities that dwarfed anything earlier sawyers had imagined. Forests began to disappear under the pressure of that demand. In the northern United States and across Canada, the great white pine stands, trees that had grown undisturbed for centuries, became targets of relentless harvest. A single mature pine could reach more than 200 feet in height and weigh several tons when freshly felled. When cut into boards, one tree could frame an entire house. Lumber companies quickly realized that the forests stretching across Michigan, Wisconsin, Minnesota, and Ontario represented a fortune waiting to be converted into planks. But harvesting timber at that scale required speed. A logging camp might send thousands of logs downstream during a single river drive. Entire hillsides could be cleared in one season if crews worked without pause. The real bottleneck came at the mill, where those immense logs had to be cut, trimmed, and prepared for transport. Water-powered mills had dominated earlier eras, but they carried a fatal limitation: geography. A mill had to sit beside a river powerful enough to turn its wheel. During droughts, the machinery slowed. In winter, the ice locked everything in place. Production could collapse for months. Steam power shattered those limitations. A boiler did not need a waterfall or a fast current. It required only fuel, scrap wood, bark, sawdust, and water from a nearby source. Once the furnace roared to life, the mill could operate wherever timber was available. This flexibility transformed the lumber frontier. Entire towns appeared almost overnight around steam-powered sawmills. Rows of bunkhouses, tool sheds, and rough wooden houses rose beside the mill yard. Rail spurs stretched outward into the forest, bringing logs in endless chains toward the cutting floor. Lumber stacks towered along riverbanks, waiting for shipment to distant cities. Production figures surged to astonishing levels. By the 1880s, some large mills processed tens of thousands of board feet every hour. A single operation might run day and night, its boilers glowing in the darkness while crews worked in rotating shifts. The air around these mills carried the constant scent of resin, steam, and burning wood waste. Yet, this relentless pace created its own form of pressure. The faster the saws ran, the more steam the machinery required. Line shafts stretched longer across mill floors. Additional saws and planers were installed to keep pace with incoming timber. Each new machine demanded greater power, and the only source capable of supplying that power was the boiler. So the boilers grew larger. Iron cylinders expanded in diameter. Pressure levels climbed steadily as engineers sought greater efficiency. Instead of operating at modest pressures, mills began pushing their boilers harder, sometimes far beyond what earlier designs had safely tolerated. But safety culture did not expand with the machinery. In remote lumber regions, qualified engineers were rare. Many boilers were operated by men who had learned the job through observation rather than formal training. Maintenance schedules were inconsistent. Inspection standards barely existed. Rivets loosened, scale accumulated inside pressure vessels, and safety valves were sometimes adjusted or disabled in the pursuit of greater output. The consequences accumulated quietly. Across timber regions, newspapers recorded a pattern that mill owners preferred not to discuss publicly. A boiler burst in one town, killing a crew of sawyers. Months later, another explosion flattened a mill dozens of miles away. In some cases, entire buildings were destroyed, their machinery scattered across the yard like broken toys. But the industry rarely slowed. Timber companies faced a race against time. Forests, once thought limitless, were already shrinking. Investors demanded rapid profit before the trees were gone. Every delay meant lost lumber, lost shipments, lost money. And so the fires continued to burn beneath the boilers. Inside wooden buildings packed with workers, pressure climbed hour after hour, feeding the saws that devoured forests and the fortunes of the men who owned them. The timber empire was rising on a foundation of steam, and the machines driving it were growing more dangerous with every passing year. Long before the sawmill boiler became a symbol of danger, it was regarded as a triumph of mechanical ingenuity. Steam power had emerged from centuries of experimentation. Early engines built in the 18th century, machines developed to pump water from flooded mines, relied on massive iron vessels heated over coal fires. These primitive boilers were crude and inefficient, but they revealed a powerful truth. Water, when heated under confinement, could release tremendous force. Throughout the 19th century, engineers refined that principle. Advances in metallurgy allowed iron plates to be rolled thicker and stronger. Riveting techniques improved. Cylindrical pressure vessels replaced the earlier square and irregular shapes that had concentrated stress along weak seams. Boilers became longer, more uniform, and capable of holding greater volumes of heated water. The industrial world embraced them with enthusiasm. Factories used steam engines to drive belts and gears across entire buildings. Riverboats carried boilers large enough to power paddle wheels against the current of major rivers. Railroads mounted them onto locomotives that hauled freight across expanding rail networks. In the lumber industry, The adoption came slightly later, but with explosive impact. Early sawmills had relied almost entirely on water wheels. When steam boilers arrived, they offered independence from rivers and waterfalls. A mill could now be constructed wherever the timber stood, not merely where water power was convenient. This freedom reshaped logging operations. Portable steam engines and boilers were hauled deep into forest regions, powering temporary mills near the cutting sites. Larger permanent mills installed even bigger stationary boilers capable of driving multiple saw lines simultaneously. The machines were simple in principle. A firebox burned wood waste, slabs, bark, and sawdust produced by the mill itself. Heat passed through tubes running inside a cylindrical vessel filled with water. As temperature rose, steam accumulated in the upper chamber. Valves directed this pressurized steam into pipes that fed engines and mechanical shafts throughout the building. What made the system revolutionary was efficiency. Waste from the milling process became the fuel that powered the machinery. Nothing was discarded. The forest fed the mill, and the scraps from that mill fed the boiler. But as the boilers grew larger, the margin for error narrowed. A vessel containing thousands of gallons of heated water at high pressure became something more than a machine. It became a reservoir of stored energy, capable of catastrophic release. The engineers who designed these systems understood the risks. Safety valves were added to release excess pressure. Water gauges allowed operators to monitor fluid levels inside the boiler. Fusible plugs, metal components designed to melt under extreme heat, provided another emergency safeguard. On paper, the system seemed secure. But paper did not control the daily realities of a frontier sawmill. In practice, the boilers operated under conditions far removed from the careful environments envisioned by engineers. They were tended by exhausted firemen working 12-hour shifts. They burned uneven fuel composed of resinous scraps and damp sawdust. Maintenance was often delayed until parts visibly failed. And most critically, the boilers were placed directly inside wooden structures filled with men. The machines that had begun as instruments of industrial progress were gradually becoming something else. In the sawmills of the timber frontier, steam boilers were evolving into unpredictable weapons of pressure and heat. To understand why sawmill boilers failed so violently, one must first understand how they were built. At the center of the system stood the cylindrical pressure vessel itself, a massive steel drum, often measuring more than 20 feet in length and several feet in diameter. The shell consisted of thick plates rolled into curved sections and fastened together by rows of rivets hammered through overlapping seams. Each rivet represented a potential point of weakness. Inside the cylinder, a complex arrangement of tubes carried heat from the furnace. Flames from the firebox passed through these tubes, transferring thermal energy to the surrounding water. As the water absorbed heat, it began to circulate through convection currents, rising as it warmed and sinking as it cooled. Above the waterline, steam accumulated. This upper chamber held the compressed vapor that powered the entire mill. Pipes connected the steam space to engines, turbines, and line shafts. When valves opened, the pressurized vapor rushed outward, turning pistons or spinning shafts that distributed mechanical energy throughout the building. Controlling that pressure required constant attention. Operators relied on gauges mounted along the boiler's side. These instruments measured internal pressure, displaying readings in pounds per square inch. A typical sawmill boiler might operate between 80 and 120 psi, already enough energy to tear steel apart if released suddenly. Water levels were equally critical. If the water inside the vessel dropped too low, sections of the metal shell could become exposed directly to furnace heat. Without water to absorb that heat, the steel would weaken and soften. A sudden influx of cooler water afterward could trigger an explosive rupture. Feedwater pumps were designed to prevent this scenario. These pumps drew water from nearby rivers, wells, or reservoirs and injected it into the boiler to maintain safe levels. Yet pumps sometimes failed. Valves stuck. Pipes clogged with mineral deposits. To prevent catastrophic overpressure, engineers installed safety valves along the top of the boiler. These valves were meant to open automatically if pressure rose beyond a predetermined threshold. When functioning properly, they released excess steam into the air with a loud, continuous hiss. In theory, they were the last line of defense. In practice, many mill operators adjusted or disabled them. A safety valve that released steam too frequently meant wasted energy that could otherwise drive the saws faster. Some firemen tightened the valves to prevent premature release, unknowingly removing the boiler's final safeguard. Over time, other threats developed inside the vessel. Minerals dissolved in the feedwater gradually accumulated along the interior surfaces of the boiler, forming a hard layer known as scale. This scale acted like insulation, preventing heat from transferring efficiently into the water. Instead, sections of the metal shell absorbed excessive heat. Those overheated plates expanded, warped, and weakened. The rivets holding them in place experienced enormous stress. Small fractures could form along seams that were nearly impossible to detect from the outside. The machine might appear stable for months. Then, without warning, the structural balance could collapse. In that moment, the boiler ceased to behave like a controlled engine. It became a pressurized bomb. Boiler explosions rarely began with dramatic warning signs. Instead, they developed through a slow accumulation of invisible damage. Every heating cycle expanded the steel shell slightly. Every cooling cycle contracted it again. Over thousands of repetitions, this constant movement weakened the metal at its seams and rivet joints. Engineers referred to the process as metal fatigue. In sawmill environments, fatigue accelerated rapidly. The boilers rarely shut down completely. Mills often ran for 16 or even 20 hours a day, leaving only brief windows for maintenance. During peak production seasons, some boilers operated continuously for weeks. Inside the vessel, minerals carried in by the feedwater hardened into thick layers along the metal surfaces. This scale created dangerous hotspots where the steel overheated far beyond safe limits. Externally, another threat loomed. Many sawmill boilers sat directly on timber foundations inside buildings constructed almost entirely from wood. The structures vibrated constantly as line shafts spun and saw blades chewed through massive logs. These vibrations traveled through the boiler supports, placing additional stress on already weakened rivet seams. Meanwhile, the fire beneath the boiler never burned evenly. Wood waste varied widely in composition. Some scraps burned slowly. Others ignited with explosive bursts of resin. Firemen often fed the furnace rapidly during busy periods, causing sudden spikes in temperature and steam generation. Pressure gauges flickered under these fluctuations. Experienced operators learned to interpret the subtle movements of those needles. A slight tremor could indicate a temporary imbalance. A steady climb signaled rising danger. But gauges could fail. Needles sometimes stuck. Glass faces cracked under heat. In poorly maintained mills, instruments went months without calibration. By the time a genuine pressure surge occurred, The warning system might already be compromised. The most terrifying aspect of boiler failure lay in the physics of superheated water. Inside the vessel, water remained liquid, even when heated far above the normal boiling point, because pressure prevented it from expanding into steam. If the container suddenly ruptured, that pressure vanished instantly. The superheated water flashed into steam with explosive speed. 1 gallon of water could expand into more than 1,600 gallons of vapor. A large sawmill boiler might contain thousands of gallons. When rupture occurred, the transformation released energy equivalent to several hundred pounds of explosive powder. Steel plates ripped apart. Iron fragments flew outward at lethal velocity. Scalding steam surged through the mill like a white-hot storm. The violence lasted only seconds. But in those seconds, entire crews could vanish. And the most chilling reality was that many of these explosions began with flaws no worker could see. A rivet hairline fracture, a hidden seam failure, a patch of overheated steel inside the shell. The machine appeared solid, until the instant it no longer was.
For the men working inside the sawmill, the boiler was both a companion and a threat. The fireman's shift began before dawn. His first task was to wake the furnace. Ashes from the previous day were raked out, exposing the iron grates beneath. Dry wood scraps were stacked carefully inside the firebox, followed by heavier fuel that would sustain the burn once the flames caught. When the fire ignited, the boiler began its slow climb toward operating pressure. The firemen monitored the gauges constantly during this period. Too much heat, too quickly, could create dangerous pressure spikes. Too little heat meant the mill would start late, angering supervisors and delaying production. Once the saws began turning, the pace intensified. Scrap wood from the cutting floor arrived in endless piles. Slabs, bark, and splintered offcuts were thrown into the furnace in rhythmic shovelfuls. The fire roared louder with each addition, sending waves of heat through the metal tubes inside the boiler. The fireman's face was permanently streaked with sweat and soot. Around him, the rest of the mill crew performed equally demanding tasks. Sawyers guided logs toward circular blades, spinning at terrifying speeds. Carriage operators controlled the mechanical platforms that shoved massive timber trunks into the teeth of the saws. Log turners used long iron hooks to reposition partially cut trunks weighing thousands of pounds. Every movement took place within earshot of the boiler's constant rumble. Steam pipes overhead shrieked as pressure surged toward the engines driving the line shafts. The floor vibrated continuously beneath the men's boots. Sawdust filled the air in golden clouds, illuminated by shafts of sunlight through the mill's upper windows. The noise never stopped. Workers communicated through hand signals and shouted commands that were often lost beneath the thunder of machinery. Despite the chaos, most crews developed an instinctive awareness of the boiler's behavior. Firemen could sense pressure changes through subtle vibrations in the furnace door. Experienced sawyers recognized the faint hiss of a safety valve releasing steam. Even the smell of overheated metal sometimes warned of trouble before gauges revealed it. But intuition had limits. A catastrophic failure often arrived without sufficient warning for anyone to escape. The men knew this. Stories circulated constantly among logging camps and mill towns, accounts of explosions that had obliterated entire buildings in moments. Survivors described iron fragments embedded in trees hundreds of yards away. Others spoke of boilers launched into the sky like artillery shells. These tales were told quietly after shifts ended, usually over cheap whiskey in crowded bunkhouses. No one doubted their truth. Yet every morning, the same men returned to work beside the furnace. They needed the wages. Logging towns offered few alternatives. A sawmill job, dangerous as it was, paid better than most labor available in remote forest regions. So the fires were lit again. Steam pressure climbed, and the men resumed their work beneath the looming steel cylinder that powered their livelihood.
The morning begins like any other shift. The mill floor already trembles with motion. Logs fresh from the river slide along greased rails toward the saw carriage. The circular blade spins in a silver blur, screaming through pine trunks thick as wagon wheels. The air smells of resin, smoke, and damp sawdust. Inside the furnace room, the boiler has been running since dawn. Pressure reads just above 100 pounds per square inch. The fireman feeds the flames steadily, pushing scrap wood through the iron door. The gauge needle wavers slightly, then settles again. Nothing appears unusual. But deep inside the steel shell, conditions are changing. A section of metal along the lower seam has weakened during months of heating cycles. Mineral scale has formed thick deposits along the interior plate, trapping heat against the steel. The metal grows hotter than the surrounding water. The rivets holding that seam expand under stress. Microscopic fractures lengthen along their edges. Still, the boiler holds. On the mill floor, the saw carriage shoves another enormous log into the blade. The machine shrieks as steel teeth bite through dense timber. Workers shout instructions across the thunder of cutting wood. Then the pressure climbs again. The fireman glances at the gauge, 110 pounds. He opens the safety valve slightly, expecting the usual hiss of escaping steam. Nothing happens. The valve has stuck. Inside the boiler, the overheated plate finally yields. The seam tears open with a violent crack. In an instant, thousands of gallons of superheated water erupt into steam. The expanding vapor rips the steel cylinder apart like paper. The explosion detonates inside the wooden mill with the force of artillery. Iron plates shear outward, slicing through beams and machinery. One section of the boiler launches across the building, smashing through the outer wall before crashing into the lumberyard beyond. A white cloud of scalding steam floods the interior. Workers nearest the boiler vanish inside the blast. Others are hurled across the floor by the shockwave. Windows explode outward. Roof beams collapse as the structure shudders under the impact. For a few seconds, the world becomes nothing but sound and pressure. Then the roar fades. Where the boiler once stood, only shattered iron and twisted pipes remain. The saws have stopped. Steam drifts upward through the broken roof. And across the mill floor, men lie scattered among the wreckage of the machine that powered their work.
When the explosion ends, the silence feels unnatural. Moments earlier, the mill had been alive with motion, belts spinning, saws screaming, men shouting above the thunder of machinery. Now, the only sound comes from settling debris and the faint hiss of escaping steam. Smoke drifts through the shattered rafters. The boiler room has vanished entirely. In its place stands a crater of broken timber and twisted iron. Sections of the pressure vessel lie scattered across the yard, some weighing several hundred pounds. One fragment has punched through a wall nearly 50 yards away. The force of the blast ignited fires almost immediately. Dry sawdust covering the mill floor catches sparks from the furnace remains. Flames creep along piles of scrap wood stacked beside the building. Workers who survived the initial explosion scramble to stamp out the fire before it spreads to the lumberyard. But their attention quickly turns elsewhere. Men begin calling out names. Some answers come weakly from beneath fallen beams. Others are met with nothing at all. Survivors stagger through clouds of steam, searching for co-workers who had been standing near the boiler moments earlier. Many of them will never be found intact. Boiler explosions produced a form of destruction rarely seen in other industrial accidents. Steel plates became high-velocity shrapnel capable of slicing through flesh and timber alike. Scalding water flashed into steam hot enough to burn skin instantly. Those closest to the rupture had little chance of survival. Outside the mill, townspeople rushed toward the wreckage after hearing the blast echo across the valley. The explosion often carries for miles, mistaken at first for thunder or a distant artillery report. When they arrive, they find the mill reduced to chaos. Rescue efforts begin immediately. Injured workers are carried away from the smoldering structure and laid out along the yard fence. Doctors, if the town is fortunate enough to have one, move from man to man, treating burns and broken bones. The dead are gathered separately. Blankets or tarps are spread across the ground as bodies are placed in rows. In some disasters, the number grows so quickly that identification becomes difficult. Clothing fragments, boots, and personal tools are sometimes the only clues left to determine who each victim was. Families begin to arrive as word spreads through the town. Wives push through the crowd, searching for familiar faces. Children stand silently beside them, staring at the wreckage where their fathers had worked only hours earlier.
Mill owners eventually appear as well, often summoned by telegraph from distant offices. They survey the destruction with a mixture of shock and calculation. The loss of life is tragic, but the mill itself represents a major financial investment. Boilers can be replaced. Buildings can be rebuilt. Timber supplies remain waiting in the forest. Within days, plans for reconstruction often begin. But for the families gathered around the ruined building, the consequences will last much longer. The machine that fueled the lumber industry has claimed another set of lives. And across the region, workers in other mills hear the news and glance uneasily at the boilers standing beside them.
After each explosion, the same questions emerge. What caused the failure? Was the boiler defective, or had it been operated improperly? Did the safety valves function correctly? Had the vessel been inspected recently? In many early disasters, the answers remained uncertain. Boilers were often manufactured by small regional foundries with varying quality standards. Records of maintenance were inconsistent. Operators rarely received formal training in thermodynamics or mechanical engineering. Investigations sometimes revealed obvious negligence. Valves intentionally tightened beyond safe limits. Water gauges clogged with mineral deposits. Pressure readings pushed far above the manufacturer's recommended levels. Other cases proved more complex. Metal fatigue, hidden cracks, and internal corrosion could weaken a boiler gradually until rupture became inevitable. Without systematic inspection methods, such flaws remained invisible until catastrophe occurred. Public outrage slowly began to grow. Newspapers reported each disaster in vivid detail, describing shattered mills and grieving families. Labor organizations demanded better safety standards for industrial machinery. Engineers argued that boilers should be inspected regularly by trained specialists rather than left entirely in the hands of mill operators. At first, many industrialists resisted. Regulation meant additional cost. Inspection programs required trained personnel and time spent shutting down equipment for examination. In competitive industries like lumber production, owners feared that such requirements would slow output. But the explosions continued. Riverboats, locomotives, factories, and sawmills all suffered similar disasters. The pattern became impossible to ignore. Gradually, the idea of mandatory boiler inspection began to gain support. Insurance companies also entered the debate. Explosions caused enormous financial losses beyond the immediate destruction of machinery. Insurers realized that preventing such accidents was far cheaper than paying claims afterward. Pressure for reform spread through multiple sectors of the industrial economy. The Widowmakers that had powered the expansion of entire industries were forcing society to reconsider how dangerous machines should be managed.
By the late 19th century, the scale of boiler disasters had produced a turning point. Engineers, insurers, and government officials began developing formal inspection systems designed to detect structural weaknesses before they triggered explosions. Boilers were examined internally and externally at scheduled intervals. Rivets, seams, and pressure plates were checked for signs of fatigue. New safety standards emerged. Improved pressure gauges offered more accurate readings. Safety valves were redesigned to prevent tampering. Water level indicators became clearer and more reliable. Operators were increasingly required to obtain licenses demonstrating their knowledge of boiler operation. In some regions, boilers had to be enclosed within protective brick structures capable of containing fragments if an explosion occurred. These measures did not eliminate risk entirely, but they dramatically reduced the frequency of catastrophic failures. Gradually, the reputation of the industrial boiler began to change. What had once been regarded as a barely controlled source of destructive power became a carefully regulated machine, one whose dangers were understood and managed through engineering discipline. Yet the legacy of the early era remained. Across timber regions and industrial towns, graveyards still contained rows of markers belonging to workers killed by exploding boilers. Old newspaper archives preserved the accounts of mills destroyed in seconds by pressure vessels that had been treated too casually. The steam boiler helped build the modern industrial world. But the cost of that power was measured not only in steel and timber. It was measured in the lives of the men who stood beside the furnace when the pressure finally broke free.